Okay, so this is now the second part of this lecture that we started, lecture number 9 on a random variable and expectation, variance, distribution, standard deviation of a random variable. But we will talk a little more about the discrete random variable, those are the ones that you can count, whose values you can count. Than anything else. We will down the road in the sequel of our course we will have actually more to say about a continuous random variable. All right. So what is the expectation of a random variable? Now when we have the story about the sample, we were talking about the sample mean. We also have an idea what the population mean is. That is usually arithmetic average of the items that you see in a sample or in a population, depending what that is. Now expectation is actually just another word for a mean, but this time the mean that we will have is the mean that is probabilistic rather than your typical arithmetic mean. So let me give you an illustration. So if you are playing a game that you would need to pay to play that game, you need to pay $2, and somebody tells you you have a 10% chance of winning, in which case you will get a payoff of $10, and if you don't win, a 90% chance you're not gonna win, you will just simply lose that entry fee that you have. I think most of the people would say, I don't want to play this game because I have to pay $2, and if I lose a game I will lose this $2, but if I win the game, I will only gain $8, right? Because you have $2 that you pay for the game, and you got $10, so basically your net gain is $8. So it's like 4 to 1, right? $8 gain versus $2 loss, while the chance of losing game is 9 times more than the chance of winning game, because you have 90% chance of losing and only 10% chance of winning. So I think most of the reasonable people that have some common sense would say, I don't want to play this game. Okay? Now, so what is the story? Well, if you just take the loss, which is -2, and the possible gain, which is 8, and you make an average, a typical arithmetic average, so which means in arithmetic average you take the 1/2 of the first number and then you take 1/2 of the second number. That's what an average is, right? You take 1/2 of each number, then you get the there will be a $3 gain on average. But of course, you know that's not the case because you're really not having equal chances. So this is not 50-50. So this would work perfectly well for 50-50 chances, but not for 10% and 90% chances. Okay, that's the key. So anytime you take any number of values that you want to make an average, you take the equal value of each one of them, equal portion, and that's your average. So for example, 3 numbers, so if you make a 3 numbers average, there will be like, let's say number 2, 5, and 8. So what is the average of these 3 numbers? Okay, well, you take a third of the first number and you take the third of the second number. That's what an average is. You take a third of the second number. This is an honest average, right? And you take a third of the third number. And that you can also write the same way. If you write that as a single fraction, you would basically add all of the 3 numbers and divide by 3, which is how most of the people understand average. But this is learned average. It's not, doesn't give you an idea what that is. And of course the average here is 5. The idea is 1/3 of the first number, 1/3 of the second number, 1/3 of the third number. That's the idea of the average. And it's the same if you add them all three and then divide with by 3. Or you have 4 numbers, you add all 4 numbers and then divide by 4. Basically you're taking 1/4 of the first one, 1/4 of the second one, 1/4 of the third one, 1/4 of the fourth one. That's how the average works. I think most of people understand the average. So for example, if you have 3 people and they need to pay something, one of them will give 1/3 of that what is needed, another one will give 1/3 of that what is needed, and the third one will give 1/3 what is needed. This is an honest average, right? So we have when we collect this money, and we'll have enough to pay that, right? That's what we usually do, what we usually mean by average. Okay, but that doesn't work here, because of course this is the case when the probabilities are not equal. So in the same manner, for example, if you have 2 friends and 3 of you need to buy a car, right? And you're gonna use that car rarely, maybe on vacation, while your friend is gonna use that every day to go to work, and the other friend will never gonna use it, maybe, occasionally when he goes with you on vacation. So what would you say? You're gonna have to give an equal amount of money to buy that car? Probably not. You're gonna say, this guy who's going every day to work with that car needs to give more. And that's the idea here. So we are not gonna take the average. We're not gonna take the average as a typical arithmetic average when we want to decide about this game. We're gonna take something that we call expectation, probabilistic average. And how that works is that, first of all, we have this distribution, so we know what's the game about. The game has a random variable. Random variable is the gain per game. It could be, the gain per game could be 8. If you win, a chance of that is 0.1 or 10%, and it could be -2, and the chance of that is 0.9 or 90%. So if you're looking for an average, probabilistic average, that is going to be -2, but you're not going to multiply this with 1/2, you're going to multiply this with 1/10. Oh, excuse me, 0.9, 9/10, right? Because that's the chance of that happening. 90% of the time you'll be losing. So this number, -2, has to have a weight, well, not 50%, not a 1/2, but a weight of 90%. And then you have the second number, which is 8, and that's the winning gain. $8, $10 you get, $2 you already spent to enter the game, so you got net gain of $8, and that is going to have to be weighted or multiplied with 1/10, because the chance of this happening is 10%. This is what we call expectation. Expectation is a probabilistic average. When the numbers that are calculated in that average are weighted by the probabilities, not equally, not 1/3 of each one of them or 1/4 of each one of them, depending how many of them are, but what is the probability? Okay, and that is going to be, in this particular case, you would have here total calculation shows up -1. Now you can check that with your calculator if you don't see it, which means that in this game you should expect, that's the name expectation about, you should expect to lose $1 per game in a long run, right? So now one game could turn this way or that way, depends, because these are random outcomes. But in a long run, when you play lots of games, you should expect to lose $1 per game. So if you play 1,000 games like this, you should expect that your loss is going to be in those 1,000 games $1,000, right? And nobody would want to play that. Yet people do play lottery all the time. Also, of course, they have negative expectation in lottery as well, but they just don't see it because they pay very little, right? So they lose very little over a long period of time. When you accumulate, that's probably a lot of loss actually. And they always play with that hope that one game could change everything, right? So this is what expectation is. Again, expectation is calculated how? Here's a formula. So we have a Latin, Greek symbol mean. That's the symbol for the expectation. And then you have to multiply every single item, every single x that you have. So if you have 2, like I have in this previous case, you multiply every single x with its probability mass. So you're weighting that x with the probability mass, maybe 10%, maybe 90%, whatever it is. And then once you're done with all of that, you'll add it all up. And that is going to be the probabilistic expectation. So when you remember this from the first half of the lecture, the triple cost of a fair coin, and the variable was the count of the heads. You can have 0. The chance of having 0 heads 1 out of 8, or 12.5%. The probability mass is 12.5%. You can get 1 head, and the chance of that's 3 out of 8, or 0.375, which is 37.5%. You can get 2 heads, and the chance of that is also 3 out of 8, or 37.5%. And then you can get 3 heads, and the chance of that is 1 out of 8. That's the only case you get is HHH, to have 3 heads. And that is of course also 12.5%, 1 out of 8, or 12.5%. These percentages here, or I shouldn't say decimal, I should say decimal number, are really by, dividing 1 with 8 or 3 with 8. Okay, so now we're gonna calculate what is the expected number of heads in the long run that you're gonna see, right? I usually, when I ask the question, I get the response, well, 1 or maybe 2. No, we are really calculating average, so you don't expect to get exactly the whole number of heads. It's going to be 1.5, and that makes perfect sense. In the long run, per triple flip of a fair coin, you're going to get 1.5 heads. Why? Because it's equally likely you're going to get heads or tails, so it gotta be 1.5 heads and 1.5 tails in a long run per game, right? Not in one game. One game you cannot get 1.5 heads. You can get either 1 or 2. But in a long run, you will get 1.5. So if you play 100 times this, you're flipping a fair coin 3 times, and then you're gonna do that 100 times. And you count the number of heads you get the first time you play that triple flip. The second time you play that triple flip, the third time, and so on, 100 times, you will see an average number of heads that you're going to get per game, per triple flip. It's going to be 1.5. And this calculation shows exactly that. So, again, how do we calculate the expectation? We have to multiply every single value of variable by its probability mass. So this is the value of variable, this is the probability mass. When you multiply it, you get 0. This is the value of variable, this is the probability mass. When you multiply that, you get 0.375. The value of variable, the probability mass. You multiply that, you get 0.75. The value of variable 3, you get 1 out of 8 times. Multiply that value of variable time the probability mass, and you get 0.375. You add this all up now, because that's the formula that to calculate. You add this all up, and you get 1.5. And it makes perfect sense, by the same reasoning I just mentioned before. Okay, so in a triple flip of a fair coin, you should expect 1.5 heads, 1.5 tails. Not in a single game, but on average, right? That's the idea of expectation, on average, in the long run. And so we usually use this word long run in probability, because we know there is something called law of large numbers. When you play that very long time, you will see that average showing up eventually. Okay, so that's the story about the expectation. What about variance, so variation, standard deviation? We have it just like in a sample. So you could have one head, you can have three heads, you can have one head, you can have zero heads, you can have two heads. So there is a variation. And most often you get one or two heads, right? 37.5% of the time. You get one, 37.5% of the time you get two. So basically 75% of the time you either get one head or two heads if you flip the fair coin three times. But there is also a chance for 25% that you're either going to get 0 or 3. So there is some variation. Now this could be a bigger variation or it could be smaller variation. So the random variable has its variation. All right. Now if you remember how we calculate the population variance for the sample, we're going to do the same thing here. But again, we will not be multiplying with the average. We're going to multiply the weights. It's not going to be the average. It's not going to be the same for every value. It will be again the probability. So if you remember how we calculate the population variance is like this. Population variance in a statistical calculation, it was a long time ago. We did this. We said you're gonna have to subtract every value you have minus the mean. You're gonna have to square that. And then you're going to sum that. And then you're gonna make an average of that. You're gonna divide it with the number of the things you have in the population. Okay, so that's the average at the end. You're dividing each of that number that is in the sum with the same thing, with the how many things you have. Okay, you're not gonna do that now. Now you're gonna multiply each one of them. So this would be the same thing here as if I multiply every one of those terms in the summation with 1 over n. Would be the same thing. Okay, but now you have a different, because one of the things happen more often than the other thing. One of the outcomes more often than the other outcome. One of the value of random variables more often than the other one. So for example, in this flip of a fair coin, 1 heads is going to happen 3 times more often than no heads. Okay? So you're not going to multiply every one of these terms in the summation with 1 over n, which you can do also at the end. You're going to multiply every one of them with its own probability mass. And that changes the formula. So the formula is basically the same as the formula we calculate the variance in the sample situation, in the population situation, but this time the weight we assign to every term in that summation is not going to be the same. It's going to be the weight depending on the probabilities. Okay, so that becomes the formula for variance. But of course, we are interested more in the standard deviation, right, than the variance. We are also interested in both of them actually, but we calculate very often standard deviation. So the standard deviation is just a radical of the variance. So this formula for variance here, just take a radical and you get a standard deviation. So that is the formula that you could use. Okay, but just like when we had the standard deviation, there is a simpler formula that you're going to use, and that simpler formula is this one here, and this is the one we're going to use in practice. It calculates exactly the same thing. So this formula here we have for a variance, formula number 1, let's call it, and this formula we have for variance, formula number 2, are calculating exactly the same thing. Now I need to do some algebra to show you that, but I'm not going into that, it's not important. You can of course, come to my office hours and I'll show you how this is equal. But in either case, if you're interested in that, but in either case, they're calculating exactly the same thing. Now, this second one is very easy to remember because this second one really shows up something that is easy to remember. You have here x squared multiply with the probability mass of the x, and then you have the summation. This is just like this formula here. The only difference is that in this formula here you're not having an x squared, you just simply have an x multiply with the probability mass and then summation. So here you have the x squared and then a mass and then a summation. It's slightly different, but you can say this is actually expectation of a square as opposed to expectation of an x. So you have an expectation of a square, and this thing of course is the square of expectation, right? The mu is the symbol for expectation for the mean we use in this formula, and now it's just a square here. So the variance in this formula number 2 is the expectation of a square minus the square of expectation. Kind of easy to remember. Sometimes people have this problem. I have an expectation and a square. Which one goes first? Which one is negative, and so on. Easy to remember. Alphabet. Expectation is before the square, e as opposed to s, right? Expectation of a square minus the square of expectation. That's it. Okay, so now how do you calculate it? So triple flip of a fair coin. What is the variance? What is the standard deviation of that game? Okay, this is what you need to do. You got all of the values around the variable. You all got all of the probability masses. That's a distribution here. This is what we call distribution, this part, right? So that is something you must have. If you don't have a distribution, you will not be able to calculate the expectation or variance. The next thing you do is to calculate expectation, because you need this in this formula, right? You have the square of expectation here, so you need to have the calculation done before you can use this formula. So again, this is 0 times 0.125, that's 0. Then 1 times 0.375, that's 0.375. So this column is just simply you multiply the first two columns row wise, right? Then the third row is 2 times 0.375, you get 0.75. This is 3 times 0.125, you get 0.375. Now you add this all up, that's 1.5. We already did this calculation, I'm just repeating it. Okay, now you need the square, all right? Square of 0 is 0. Square of 1 is 1. Square of 2 is 4. Square of 3 is 9. So these are the squares of the variable x. So the x is 0, 1, 2, 3. But in this formula, as you can see, you need the square of x. So you need 0, 1, 4, 9. Okay? And now you do the same thing again. You're going to multiply the probability mass with a square to get the expectation of a square. So when you multiply px and x squared, you got the x squared times px, or px times x squared is the same thing. So you're multiplying 0.125 times 0, which is 0. 0.375 times 1, which is 0.375. 0.375 times 4. Okay, that is actually 1.5. And then 0.125 times 9. When you do that properly, you end up with 1.125. Okay, now you add all of this, because you have to get this first half of the formula, this piece, sum. Okay, so you add all of that, so you get sum of x squared times the probability mass, and that is 3. And now you use the formula number 2. Formula number 2 says the variance is equal expectation of a square, which is, I just calculated, 3, minus square of expectation. The expectation is 1.5. The square of expectation will be 2.25. You can square this. And you end up with subtracting 3 minus 2.25, which is, check with your calculator, 0.75. That's the variance. Now, if you're interested in standard deviation, of course, you're going to have to take a radical. And radical will be approximately 0.866. Okay? You can do this also with your calculator. That's, a way to avoid work, right? So you will need to know this formula though. But you can use this calculator. And I have my calculator. What do you need to do in the calculator? Right. You need to have the distribution table. Distribution table is necessary. All right. So you're going to enter the statistics. You're going to edit there. So you enter the edit. And I have something in the list 1, so I'm not going to change it. I'm going to put the distribution in list 2 and 3. So I have to have 0, 1, 2, and 3. 0, 1, 2, and 3. That's the first column. Okay? So that's the value of the x's. The second column is the probability mass column. So I have to have here 0.125. You can just write 1 out of 8, right? 1 divided with 8. Your calculator will figure this out. But since I already calculated, I'm going to write 1.125. That's 1 out of 8. And then the second value is 0.375. Then the third value is 0.375 again. And the fourth value is 0.125. Those are the probability masses relative to the value of the variable, which means this row must be, they are related, of course. You can't miss one value, you're going to get something wrong. So now remember that my probability distribution here is in the L2, L3, the two lists in the calculator. So I go back to statistics. I want to calculate now. Calculate. I am going to calculate one variable statistic because I have only one variable, the count of heads. But I am also going to say, where is this variable? In list 2. So I had to change this because the value of the variable is in the list 2. Now you add a frequency list. This is not now frequency list as you know in the statistic. This is now relative frequency. Or should we say, these are the probability masses, probability mass or relative frequency. So you have to put that. That's list 3. If you don't put that, you will get just your regular sample calculation, which is not the case here. You have probability calculation here. And now you can calculate. And you will see we got the same thing. Right there on the top, you get a mean. Your calculator really doesn't know how to write Greek symbol me, so it uses this statistical symbol x bar. But that is also the same thing here. We have probabilistic mean, or we call it expectation. Pay attention to that. So your calculator doesn't write mu, it doesn't write this Greek symbol that we use. We use Greek symbol for a mean, this symbol, Greek m. Your calculator uses statistical symbol x bar, but it means the same. Then you calculate the sum of x squares, that's 3. That's the, I don't know what it is. Well, I don't even know what that means, but I'm not going to be bothered by that. I have here calculation of the standard deviation. You can see here. The sample standard deviation doesn't exist here, okay, because we don't have a sample. Your calculator knows that. Now it calculates standard deviation and it gets the same thing I got here. I used 3 decimals, so I took the radical of 0.75, got 0.866. You can see that number here, 0.8660, and so on. So if you put a 0.75 and you just take the radical, which is the second button here, I need to do that in proper order. So I have the radical and I have 0.75. So that's what I did. And you calculate that, you get exactly the same number, right? So that is what your calculator is going to give you. So you have to see that in your calculator. So we have to be really careful about this story here. I don't need to know all of that stuff. I do want to go back to that just to make it clear what is the rest of that stuff here. So again, this sum of x squared is really not a sum of x squared, because if you sum the x squared, you're gonna have what, 14 here. This seems to be weighted. This is a weighted thing. This is the actual expectation of a square, which is 3 here, right? So that's the meaning here. Oh, okay. The minimum is 0. Okay, I understand that. That's really not very relevant for us. The minimum is 0. The maximum is 3. The median is 1.5, the average of these two, right? And the quartile 1, quartile 3, we don't need that. But that's what your calculator is also capable of doing. Okay, good. Now this is the calculation you will do. Okay, let's go back to the example of the accidents. You remember that story we had in the empirical distribution? I come up with this distribution, which we said the number of accidents per day in Adams County, Pennsylvania. We have 2, 3, 5, 6, 7, 8, and 10 accidents possible. And you have 5% chance on a given day to have 2 accidents, 10% chance to get 3 accidents, 20% you get chance to get 5 accidents, 1/4, 25% chance to get 6 car accidents, 20% chance to get 7 car accidents, 10% chance to get 8 car accidents, and 10% chance to get 10 car accidents. Okay, so I have this distribution. This is the distribution. The number of accidents on any given day in Adams County, Pennsylvania. That's a proper name for the random variable, but I just made it shorter here. It's in the context. X is in the first row. The probability mass, or the probability of that could happen, each one of them, is in the second row. Okay, this is nicer to write the course vertically, but I didn't bother that over there because I had it. I didn't intend to do anything else with that. Okay, but now I need to really have that vertically. So this is the number of car accidents. This is the probability mass of each one of them on any given day. So that's again, this is the table which we will use to calculate mean and variance. This is a distribution. So again, if you're going to calculate mean and variance, expectation and variance and standard deviation of a random variable, you need to have a distribution of that random variable. If you don't have that, you can whistle. You're not going to be able to calculate. First, mean, the expectation. The common sense is we want to know on any given day in the long run what is the average number of car accidents you're going to have. Okay, so some of those numbers are more likely than the other and so on, but on average. So that's the expectation. Expectation stands for the probabilistic average. What should you in the long run going to have? What is going to be the average number of car accidents in the long run? So we have a very simple formula. So again, the first two columns have to be multiplied row-wise. So you get 2 times 0.05, which is 0.1, 3 times 0.1, which is 0.3, 5 times 0.2, which is 1, 6 times 0.25, which is 1.5, 7 times 0.2, it's 1.4, 8 times 0.1, it's 0.8, and 10 times 0.1 is 1. And you have to sum it. That is the formula. Again, every value of the variable times its probability mass, sum all of the terms you got. And you sum all of these guys, you got 6.1. This is, so it's written down there, but I'm going to emphasize this. So you have a highway department, you tell them, oh, we did this little itsy bitsy calculation, we didn't have that many days, so it's kind of not very precise, but we have something. We can tell you in a long run, you should expect about 6.1 car accidents on any given day. On average, you're going to have 6.51 car accidents. That's important information, because if your administration in that county, you definitely want to know how you're going to staff your emergency services, because that's what goes with car accidents. Like police, maybe fire department, they are usually needed, or ambulance and stuff like that. If you have 6.1 car accidents on a given day, that is important information. So you're going to use some experience or some information from some other places that can tell you what you need to do. Okay, but you also need to know the variation, the variance, the standard deviation. Because why is that important? Because I need to know, is this going to wildly vary? I'm going to have one day nothing and another day 20 accidents, stuff like that. That's important. Or I always get like a 4, 5, 6, 7, something like that, right? The variance is very important to know what the variation is. So that's why we calculate the variance. So how do we calculate the variance again? So we go again the same table. We have the x squared here, x squared. So you get this 2 squared 4, 3 squared 9, 5 squared 25, 6 squared 36, 7 squared 49, 8 squared 64, 10 squared 100. Those are the x squares. Now you need to get the expectation of a square, which means you're going to use the probability mass and a square of x, and you want to multiply this. And that goes in the last row. Row wise, okay? 0.05 times 4 is 0.2. 0.1 times 9 is 0.9. 0.2 times 25, that's 5. Use your calculator if you don't see. 0.25 times 36, that's 9. 0.2 times 49, it's 9.8. 0.1 times 64 is 6.4. And 0.1 times 100, that's 10. That's easy to calculate even without calculator. So these are all of the terms that you need to have in the expectation of a square. To get an expectation of a square, you add them all up, 41.3. So that is the expectation of a square. I almost wanted to write the variance, but it isn't variance, okay? This is the expectation of a square. So what's the variance? Well, variance is, I know it's written here in this sentence, but I'm going to write it down piece by piece as I'm saying it. Variance. We don't have a special symbol for variance. We just use standard deviation square, because that's the relation between the variance and standard deviation. And again, here, we don't have a population and sample. We just have one random variable. And if you want to refer to something, you can consider this population. It isn't a sample, that's for sure. Although I have made this distribution by using a sample, but that's a different story. So what we have here is the expectation of a square. That's our formula. So the formula goes expectation of a square minus the square of expectation. The expectation of a square is 41.3 minus the square of expectation. Here's an expectation. Let's hear it one more time, right? That ought to be squared and subtracted. Alright? So now when you do the proper calculation here, you end up with 4.09. I'm going to leave that to you to check with your calculator. That is variance. If you need standard deviation, you're going to have to take the radical of that. Like standard deviation is always a radical of variance. Variance 4.09, radical. Well, of course, you're going to have approximation because there's going to be lots of decimals. and I have my approximation is 2.0224. You can say 2, okay? So you can say to your boss, hey, you're gonna have approximately 6.1 car accidents, give or take 2, right? Which means that there is a standard deviation that they can go 2 above and 2 below. You remember what standard deviation meant for in terms of a sample. That's approximately the average jump away from the mean. That is similar thing here. Although we have a little bit a probabilistic notion of that. So in a so-called normal distribution, a distribution that are most often in nature, this would mean that we would have approximately 2/3 of the time anything between 4 and 8 car accidents. So we give or take 2 car accidents. The average is 6.1, but give or take 2. So you can go down 2, you can go up 2, so you can go down to 4, you can go up to 8.1 something. And this between 4 and 8.1 something is going to happen 2/3 of a time, 2/3 of time, which means that it's still possibility to go even higher or lower than that. So we have this range between, so if you subtract 6.1 minus 2.02, that would be approximately, I'm going to pretend like I got some calculation here done, 4. And then on the other side, in the middle of the range, you have the mean, 6.1, and the upper end of the range is going to be like 8.1 approximately. Again, I'm not doing any precise calculation here. So this is the range of car accidents you're going to have 2/3 of the time. 2/3 of the time. Okay, that's the idea in a normal distribution. All depends on the distribution, of course. This is an interesting thing to know, right? So the administration of this county need to know that, right? Well, and that means that we have to be able to handle, well, at least 8 car accidents. So maybe we need to have some kind of reserve situation, some kind of reserve force that we could engage in case, workforce that we could engage in case we have some really bad situation, right? So that's an important thing about variance, right? So whenever we talk about probability of sample or population, we always consider these two very, very important parameters. The mean tells you what's an average, and the standard deviation tells you how far you can go up and down. Okay, and that doesn't mean that this is the maximum. No, that's the story about range. But it gives you an idea of what most often you should expect. How far you're going to go up, how far you're going to go down. And that's an important information because it could be very little, it could be also big difference, depending on the variation. So, okay. So, again, I am done with this story. You guys should check homework on this and calculate yourself. By the way, you definitely could use a calculator here again, and if you want to use a calculator, you're going to have this distribution in your calculator. So maybe I should do that. Okay, so if you want to do that by using calculator, you have to put up that distribution in your calculator. So I'm going to use L4 and L5, list 4 and 5. So I have 2, 3, 5, 6, 7, 8, and 10. 2, 3, 5, 6, 7, 8, and 10. Right? As I said, this is not really a great sample because in the beginning I had just 20 days. And then I have 0.5, 0.1, those are probability masses, 0.2, 0.25, 0.2 again, 0.1, and 0.1. So it's a list. You gotta remember that It's a list 4 and list 5. And now back to statistical calculation. One variable, the number of car accidents on any given day in Adams County, Pennsylvania. That's the name of the random variable, the meaning of X. List 4, the probability mass is in so-called frequency list. The probability mass is actually comparable or compatible with the relative frequency in the population. So that's why it's called that way. And now calculate. And you will see that you get, oh, I think I have something wrong. This is obviously something that I messed up. Let me check it out again. So I have 2, 3, 5, 6, 7, 8, 10. 2, 3, 5, 6, 7, 8, 10. And then I have in the second line 0.05. Obviously mistake. Easy to make. So you have to be very careful. 0.05. Did I miss 0 or I just didn't put it in? One way or the other. It was a mistake. The rest of them is okay. I have 0.1, 0.2, 0.25, 0.2, 0.1, 0.1. That's looking all good. So I had in the first row 50% as opposed to 5%, which I should have. Okay, let's go back to check this again. One variable statistics, I have them properly. Or this I also put here L4, I should have L5, right? I'm doing things fast, and that's never a good thing. You can only catch flies fast. All right, so okay, so now I have it. You can see 6.1. That's the mean. It's written in a statistical language like a X bar, although we use the Greek symbol mu, m, Greek m. And you have this standard deviation. It doesn't give you variance. You want to have variance? Square it. Okay? It gives you standard deviation 2.02237, so on. And that's exactly what we got here. The radical of variance is 2.0224. Yeah, I got the same 4 decimals, right? This is more precise. And then some information about the quartiles, which we don't need. All right, so you can use your calculator here. Okay, now I think I'm done. I'm going to leave you to check the homework. So that is important because you're going to learn how to, get some routine how to calculate this table. Is important to remember. So you have the x's, you have the probability masses, you have the x time its own probability mass, the sum is an expectation, then you have x squares, and then you multiply probability mass times the x squares, you get the fifth row. When you sum that, you get the expectation of a square. So if you want to call this expectation of x, this guy here would be expectation of an x squared. That's also variable, right? Yeah, on a random day, oh, it happened to be 2 accidents. Well, okay, so on that random day, it happened to be a square of 4 accidents. Nobody used that random variable, but we do use it in the formula, so it's an expectation of a square. That's 41.3 here. So if you can remember this table, you can always do that. Again, of course, obviously, two first column in the table must be the distribution. Without knowing distribution, you can calculate nothing. And with knowing distribution, you can calculate everything. So this is important. Okay, I am going to end this stream, the video, and you guys are going to check it out and do the homework. All right? And I'll see you the next time we meet for the next lecture.